Evening all, and welcome to our live seminar on the Unit 2s. So I have got the chat window up in the corner of my screen, and if any of you are going to be posting anything that is inappropriate, then you will be put in a wonderful little timeout for a while. If you carry on, then I'll just block you, quite simple. So let's all try and remember that we do need to be polite to each other and obviously just revise together for a bit. So I've been watching the chat window, and obviously I've picked up on the great many different topics that you've given me a nice list of. So I've got a big list here already of all the different things that you want me to go through. So I figure we're going to start off with the physics, because that's the one that most of you seem to actually want to go through here. So what we're going to do is start with the physics. Then it seems like there's only a few bits of chemistry and biology people want to go through. So we'll go through as much as we can, but we're not going to stay here all night because you lot need to sleep, and I would actually like to have some kind of a live tonight as well. So if there are any things you want me to go through, then post it in the chat window and I'll have a little look at it as we go through. But as I say, physics first of all, then we'll come on to the chemistry and the biology. So with our physics then, the first thing we need to think about is basically generating electricity. So what we've actually got then is we need to think about photocells first of all. So with the photocells, in terms of what we're actually seeing happen is light energy is being transferred into electrical energy. And we need to remember that what we've actually got is a direct current being generated. Okay, so what we have, DC, stands for direct current, and that does come out every once in a while as a little 1-mark question. So by direct current, we mean the one that's going to be produced in the same direction all the time. For those of you doing the higher tier paper, you need to know how it actually does this. So the photocells then are made of silicon, and as the light actually shines onto the silicon itself, then what it does is it knocks an electron out of the silicon atom. Those electrons are then free to flow, and that's what generates the current. So what we find is that there are 3 ways that we can actually increase the output from our photocell. First of all, we can increase the light intensity. Bit hard to do if we're talking about the sun. Secondly, and the most easy way to do this, is increase the surface area, or we can reduce the distance between the light source and the photocell. So that's only if you're doing high that you need to know that. If you're on foundation, all you need to know is it's light energy into electrical energy, and it's a direct current. Now, what we find then is that the big advantages of using these photocells, first of all, they're low maintenance. So once you've actually put them in place, then you don't have to do anything with them. They last a really long time, and they don't actually need a fuel to be burnt. So that means we're not actually producing any carbon dioxide, which is one of the biggest problems that we've got in terms of our electricity generation today. So we also have a renewable energy source there from the sun, which means that if they ask you that question about how would you define a renewable energy source, it's one that will not run out. Okay, don't write down other random things about recycling and whatever other random phrases you want to use, because you won't get a mark. Literally just say it's a source that does not run out. The big advantage is that we can actually use them in very remote locations. So in the middle of Australia, in the middle of a desert, whatever you fancy, you don't have to be anywhere near a power station, because we don't have to have power cables going from the actual source the electricity is generated to the home it needs to be used in. There are some big downsides though. First and foremost, it only works when the sun shines. So literally they do ask this question quite often about what are the disadvantages of using photocells. If you say they don't work at night, then you get a mark. The other one that you can say is that you need a large area in order to actually generate a significant amount of electricity there. Some other sources of our solar energy then is that we've got passive solar heating. So that's where you can build houses with these really big windows on the south side, because what we then find is the sun shines into the building, it's absorbed by the surfaces inside and then radiated out. So what we actually find there is it will warm up your house without any need for obviously heating itself. Solar stoves are a way that we can actually cook food. So you have a nice curved mirror and a little pot in the middle with your food. All it does is it reflects all of that energy onto the little pot in the middle, and therefore cooks the food nice and simply. Solar thermal towers are going to work by having a whole range of different mirrors at the bottom, and they all focus on one point at the very top of that tower. Now, that is going to heat up to very, very high temperatures, potentially up to 500 degrees Celsius, which means that we can then heat water into steam. And that steam can be used for a whole range of different things then. For those of you on the higher tier paper, bear in mind the fact that we have those mirrors on actual motors. So as opposed to being fixed in one position, what they'll be able to do is actually follow from where the sun is, and therefore keep it focused at its maximum intensity at the top throughout the entire time. Now, in terms of another way we can use energy from the sun is via the wind. One thing to remember is that when we're thinking about wind turbines, wind itself is generated by the sun. So as the actual sun heats up different parts of our atmosphere in different levels, we get those convection currents, and that's what the wind actually is. It's the movement of the air. So what we find is that's going to be using kinetic energy and changing it into electrical. Again, advantages that we've got, it's renewable, so it means it's not going to run out anytime soon, and it also doesn't produce any waste. So that means no carbon dioxide increasing in the atmosphere. Disadvantages, as always with these things, go with spoils the landscape. Then you could also talk about the fact that the wind speed's got to be right, and the fact that we need a large amount of space in order to generate the same amount of electricity as we would in one power station. As I mentioned earlier with the photocells, what we have is direct current, but there's the other version of our current, which is the alternating current, or AC. So remember, if it asks you what AC or DC mean, DC is direct current, AC is alternating current. Now, what we actually find is that this leads us really nicely onto this idea of the dynamo effect, which is something that a couple of you have asked me to go through tonight. So in terms of the dynamo effect, what we actually have is the basic version. You've got a magnet, North Pole, South Pole, and in between you have a wire. Okay, so what we actually have between the North and the South Pole of the magnet is a magnetic field. Now, as you move a wire through a magnetic field, you induce a voltage. Okay, so that's the real basics of it, is that all you need is a magnetic field and a wire, and as long as either the magnet is moving or the wire is moving, you induce a voltage. If you want to increase the size of the current that you are actually generating, then what you can do is you can either use stronger magnets, you can have more turns in the wire, so basically use a coil as opposed to a single strip of wire, and you can make the wire move faster. So any of those three would get you marks if they asked you how to increase the size of the current generated. Now, when you are thinking about your little generators here, it's generating alternating current. Okay. Now, the reason it generates an alternating current is if you imagine that you've got a coil of wire and it's spinning, then what's going to happen is you're going to have it positive, and then as it turns through 180 degrees, it becomes negative, and then as it turns all the way back, positive again. So it literally changes between the positive and the negative, which then gives you that little wave that's very indicative of our alternating current. Okay. When we're looking at generating electricity, what we need to remember is power stations are still our main source of doing this. So what we have are a lot of different fuels that we can actually put into a power station in order to generate the heat needed to make the steam, to drive the turbines, etc. So what we're actually going to do then is you're going to start off with something in a furnace. Then when you burn the fuel, what we're going to find is that you then generate heat. Heat turns water into steam, steam drives the turbines, turbines turn the generators, and generators make the electricity. So what you find is that everything after the water turning into steam is exactly the same no matter what the fuel actually is. So really simple, just remember something is going to be burnt at the beginning, that generates heat, okay? That's the only bit that changes. And the next thing that you will have is going to stay the same, whether it's fossil fuels, biomass, nuclear, makes no difference. So what we actually have then is, once you've got the heat, water's changed into steam, steam turns the turbines, turbines turn the generators, generators make the electricity. Okay. Now, once we've got that electricity, we actually need to transport it around the country, and we do so through the national grid. So the national grid itself is just that whole series of pylons and cables that you can see literally going all over the countryside, and that quite simply is going to transport the electricity from the power stations to all the homes and industries around the entire country. Okay. We then come really nicely onto one of our first calculations of P2. The nice thing about P2 is that we actually have lots of calculations. So what we have first of all on page 2, our calculation sheet here, only the orange ones are important for the unit 2s. The ones in green at the top were used on unit 1. You can ignore those now. It's the unit 2s right there in orange. Okay, so what we're going to be using first of all then is our efficiency calculation. Now, in order to do the efficiency, hopefully remember useful energy output divided by the total energy input, and then because it's a percentage, times your answer by 100. Okay, so what you are then going to do if you're on the foundation tier, basically stick the numbers in, put it in your calculator, write down the calculation first of all, in case you manage to mess up on the calculator, and then secondly, your answer. If you're on the higher tier, they need to make it a little bit more of a challenge for you. So what they're actually going to do is they're going to give you the efficiency and either the useful energy output or the total energy input. And so what you're then going to do is rearrange your equation. Okay. Now, if you're doing the higher tier, in theory, you're quite good at maths as well. So that shouldn't be too much of a challenge for you. Don't forget to put a calculator in your bag now, okay? If you don't have a calculator, you're not going to be able to do most of the calculations. So don't forget the calculators tomorrow because you're throwing away an easy mark. So once you've calculated the efficiency then, that's your first calculation, and that's been on every exam paper so far. So since 2012, every single exam paper has had the efficiency. Okay, so if you do that, that's going to be 2 marks for you out of the 25 in the physics section. Next one that we come on to is obviously the big problems of using any of these wonderful little coal burning, fossil fuel burning power stations is they generate carbon dioxide. Now, carbon dioxide is a big problem because it leads to global warming. Now, global warming is quite simply where basically the Earth is warming up. So what we have are these greenhouse gases, of which there are 3 that we need to remember. First of all is going to be water vapor. Secondly is methane. And third is carbon dioxide. Okay, so what we actually have then are those 3 gases. And so they can all lead to extra infrared radiation being trapped in the atmosphere. Okay, and that means that the world is going to heat up. Okay, now for the higher tier, you do need to know that in a little bit more detail. If you're doing foundation, just remember methane, carbon dioxide, water vapor. If you can only remember 2, it shouldn't be too much of a problem. Generally, they only want you to answer 1 example. So what we've actually got for the greenhouse effect for the higher tier then is that you've got to talk about the fact that shorter wavelength electromagnetic waves, and that'll be infrared, are going to come down from the sun and pass through the atmosphere first of all. Now, once that radiation reaches the Earth, it gets absorbed by the actual surface, and then it re-radiates this longer wavelength infrared radiation. Those are then absorbed by the gases within the atmosphere, and that means that the world is going to heat up. Okay, so that's the higher tier version, is just understanding the fact that the Earth is going to re-radiate the longer wavelength infrared radiation. One of the things that they will talk about is the fact that climate change is either man-made or natural. And they quite like to give you those random little badly drawn people on the exam papers with 2 little speech bubbles arguing about things. So what we actually have there then is you'll have one sitting there saying about climate change being man-made and the other one arguing that it's natural because it goes in cycles. Now, all you need to do there is compare their 2 arguments and basically just give your reasoned judgment for it. So yes, there is some evidence, the fact that it does go in natural cycles of warming, but we are increasing the carbon dioxide levels due to deforestation, due to the fossil fuel burning, and we know the effects. So obviously, read the question, look at the information they give you, and then answer it effectively. And yes, that was the greenhouse effect. We then come on to our second calculation, which is all about power. Now, this one could very well be one of these 3-mark calculations, because what we find is that the calculations we're coming on to now are actually all linked together. So they could very well give you part of the actual information, but not all of it. So we're going to be looking at these two calculations here. So power is voltage times current, and energy supplied is power times time, first of all. So what we will do is foundation tier, again, they're quite likely just to give you the voltage and the current and ask you to calculate the power. If you're on the higher tier, probably going to be a whole lot of rearranging equations once more. But as usual, stick in a little triangle as we've done in class, and then what you can actually do is rearrange it nice and easily. Okay. Now, once you've calculated the power, you can then work out the energy transferred. And what they will sometimes do in the question is they will actually ask you to calculate the energy transferred, and in the question itself, it will tell you the voltage, it will tell you the current, and it will tell you the time. Now, if you literally look at page 2 and try to find one that has energy transferred power, energy transferred voltage, current, and time, it's not going to be there. You've got to do the two calculations one after the other. Okay, so what you need to actually do is voltage times current, first of all, gives you your power, and then times that by the time to give you your energy transferred. Okay, just look at those, and usually they're given away by the fact they're worth 3 marks instead of 2. Okay, the other one that they could put in here to make it a 3 marker is to calculate the cost of the electricity that you're using at home. So this uses the energy transferred, and then you just multiply that by the cost per unit, which it tells you in the question. Okay, so all you do there is calculate your energy transferred using obviously whatever information they've given you, times that by the cost, usually going to be 10.2 pence, and then that gives you your cost of using a kettle for 3 hours or whatever it is. Those of you doing the higher tier do need to know about this thing called off-peak electricity. Now, that's basically where some electricity companies actually offer you the option of signing up to a tariff that gives you cheaper electricity in really ridiculous hours of the night. So basically what it means is that you could use your cheaper electricity to heat your homes, to run the appliances, to do your washing, whatever it is you like. The big downside though is the fact that these are not at good times. It's not like it's midday or anything like this. We're talking about it being 3, 4 in the morning. Now, not many people are going to be up and wanting to do their cooking, their washing and things like this. So you need to have timers on your appliances, and not everything is going to be able to be carried out at that time. Okay. Now, also on the higher tier, we need to know about transformers. Okay. Now, we're not talking about the robots from the films. Okay. What we are doing is looking at the actual power stations, and then the transformers are the devices it goes through before being transmitted through all those cables. So what we actually have is the actual power station is going to generate electricity at a certain voltage. But what we're going to do is put it into a step up transformer, first of all, and that increases the voltage to about 400,000 volts. And then it's transmitted through all those cables, because the higher the voltage, the lower its resistance, and the less energy we lose as heat. So what we actually find is that as a result of increasing the voltage, we have less energy being lost in its actual transmission. When we then get to near our industries or our houses, obviously we do not want 400,000 volts coming into those, because let's face it, a few more people would be stupid enough to get themselves killed. So we have the step down transformer, which decreases the voltage down to the safer levels. So just remember that there are those transformers that will either increase or decrease the voltage. Just look carefully to make sure that if it specifies how can you increase the voltage, that you say step up transformer. If it just says how can you change the voltage, transformer is enough. Now, what we also need to understand then is about our power lines. Some of them we know are overground because you can see them, but beneath the ground, we'll also bury a whole load of them, particularly in towns and cities. So you don't tend to have the big pylons going through the middle of the town centre, because obviously things are going to collide with it. So what we have is in towns and cities, we bury them underground, which means there's no visual impact from them. And it also reduces the risk of things being actually colliding with them. Now, the big problem of that is it's more expensive to bury them underground. You've got to insulate them, you've got to waterproof them, because obviously we all know electricity and water don't mix well. And if something goes wrong, you've got to dig it up. So that means that wherever the problem is, You've got to dig up the road, the pavement, whatever it is, in order to fix it. And that can actually produce some big problems. Now, in terms of our fossil fuels, hopefully we all know there are three: coal, oil, and gas. You don't have to say natural gas. Gas is absolutely fine for the marks. Remember that all fossil fuels were actually formed millions of years ago, and the reason that they're called fossil fuels is because they do take millions of years to form, which is also the reason that they're going to run out, and that's why they're non-renewable. So if they ask you about the fact that some fuel types are non-renewable, then what we actually find is that if it's non-renewable, you need to say that that means it will run out. Okay, so what we actually need to specify there is, anytime they say what does non-renewable mean, it means it's going to run out. Okay, now folks in the chat, can we actually be sensible rather than just posting random things? Because I am trying to monitor that at the same time as doing this, and reading things that are just completely irrelevant doesn't really help anyone. So what we've then got, some disadvantages of fossil fuel burning power stations then. First and foremost, we actually have a big problem of carbon dioxide. So if we are doing a lot of burning of fossil fuels, then what we're going to find is that carbon dioxide is produced in large amounts. So what we actually find as a result of the carbon dioxide being produced in large amounts, that's going to lead to global warming. Okay. The other big problem we've got is we actually have to then transport all these fossil fuels that we're digging out of the ground, which can be problematic if we're talking oil, because oil spills, as we all know, are very problematic for the environment. In terms of our advantages of fossil fuels then, it's reliable, it's established, we've been using it for a really long time, and it produces large amounts of electricity. Obviously, one of the big downsides of that is fossil fuels will run out at some point, so they're finite resources, there's a limited amount left, and they produce a lot of carbon dioxide, so it's not brilliant. One option that we can use that's a bit better is biomass power stations. So biomass power stations then are using something that's come from living organisms. So what we actually find is this is using something like wood, straw, you can have alcohol, which has come from sugarcane that we've fermented, anything like this at all. Okay. Now, the big advantage of using biomass is this thing called carbon neutral. Now, all that means is that when the plants are actually growing, they absorb carbon dioxide from the atmosphere, and as a result of that, when we burn them, they release the same amount. So there's no net gain in carbon dioxide. Literally, as the plants grow, take carbon dioxide out of the atmosphere, and then when we burn them, they release the carbon dioxide that they took in. So it stays the same. There are some pretty significant downsides though. We are still releasing carbon dioxide, which is a problem. And the other big problem is that some countries will actually choose to grow these biofuels instead of food. So you can have food shortages in some poorer countries because what they're actually doing there is growing the biofuels which they can sell for more money, and it's at the expense of food production in their country, unfortunately. The other option that we can go on to is nuclear power. So nuclear power plants, this links really nicely to those of you in year 11 who are obviously doing core and additional at the same time. Then this links into P4 really nicely. Okay, so what we actually have is inside the nuclear reactor, you've got either uranium or plutonium. Now those are the fuels. So foundation tier paper, they do like to ask you on one of them what the fuel inside a nuclear reactor is. Uranium or plutonium gets you the mark there. Now, what we see is a nuclear fission reaction, and as a result of that, we're generating a lot of heat. So the heat that's generated from that nuclear fission turns water into steam, steam drives the turbines, turbines turn the generators, generators make the electricity. So as I said, everything about power stations is exactly the same, except for how we generate the heat in the first place. Now, one downside about our nuclear power plants is that uranium is non-renewable fuel. It's just that we've got thousands of years of it until it's going to run out. So we're quite happy using nuclear fuel for that reason. And another big advantage that we've got there is the fact that we don't make carbon dioxide, but we do make radioactive wastes. Two types, you've got high level and low level. Your low level radioactive waste is pretty straightforward. Just chuck it in a landfill, no one really worries. High level waste is the problematic one. That one is going to stay radioactive for a long time. Okay, we're talking millions of years here. So what we actually do is we encase it in glass and bury it deep underground away from any water sources. So remember the differences between the ways we deal with the high level and the low level radioactive waste there. One thing that we can also do with the radioactive waste is reprocess it, which means that any of the unused uranium is going to be put back into the reactors. But one of the waste products from that process is plutonium. Now, the big downside about generating plutonium is the fact that we can then use that to make nuclear weapons, which obviously could be problematic if the wrong people get hold of it. Big benefits, though, for using nuclear power. Number one, we generate an awful lot of energy from 1 kilogram of fuel. Okay. Secondly, it's not going to run out for a really long time. And finally, what we've actually got is no carbon dioxide being made. Those of you on the higher tier paper will also need to know the disadvantages. So first one is that the cost of building a plant and decommissioning it are very high. We'll also have to process the fuel before we can use it. You can't just dig uranium out the ground and just chuck it in and hope it all works well. And we have the risk of accidents. Think Chernobyl, think Fukushima, okay? All of those are problematic. Which then leads us really nicely from nuclear power onto the radioactive decay and alpha, beta, and gamma radiations, okay? So first of all, when we're talking about radioactive decay, then what we're looking at is the nuclei of some atoms actually breaking down because they're unstable. So what we find then is we will have one of three types of ionizing radiation being released: alpha, beta, or gamma. So alpha and beta are particles and gamma are rays, okay? So what we actually have then are three types of ionizing radiation that we need to know about. And one of their favorite questions to ask you in the physics section, particularly when it comes to the 6 markers, are about alpha, beta, and gamma radiation. So you've all seen that delightful little picture they give you, which has got the different particles and the arrows showing how far they actually penetrate through materials. So you've got a few sheets of paper to start with, a thin bit of aluminium, and then a thick bit of lead or concrete at the end. And what they could do as a common question here is they're going to give you a table of results telling you what's actually being passed through the different materials and ask you to identify which source of radiation you actually have. So the least penetrating is alpha radiation. So that's the one that's stopped by a few pieces of paper. Then the beta is stopped by a thin sheet of aluminium, and gamma is only stopped by the lead or concrete. So what you find is that alpha is the least penetrating, gamma the most penetrating. So they go in order. However, as people have pointed out in the chat there, what we're talking about at the same time is how ionizing they are. So if you think about alpha being the least penetrating, it's the most ionizing. But gamma is the most penetrating and the least ionizing. So what we actually find then is that we have those two patterns we need to remember. Okay, so they could ask you to apply that rather than just literally sit there and tell you about what the different radiations are. As I say, generally they will give you some kind of experiment results and then they will ask you to identify what kind of radiation it is. Now, the big problem of these ionizing radiations is that if it comes into contact with atoms, then it causes either the addition or the removal of electrons. Okay, so when you either add or remove electrons, what happens is we make an ion. Okay, so what we end up with if you're removing electrons, and remember an electron is a negative subatomic particle, then we make a positive ion. But if we add electrons, then it becomes a negative ion. If we're talking about the actual effects of our ionizing radiations on the human body, for example, then the easiest answer you can give there is it causes cancer. That will be a guaranteed mark every time. It's basically going to be ionizing the cells, which causes damage and kills them. Okay, so if you're doing the higher tier paper, you need to know how. It's basically that the DNA is ionized, and then as a result of that, it can be damaged and lead to cancer or cell death. Okay. One of their other favorite questions about the radiation is literally how we can handle it safely. So they will ask you about a science teacher using it, or they're going to be asking you about someone in a hospital using it, for example. So what we actually have as a result of that is some different techniques we can use to minimize our risks. First of all, you can wear protective gear. Okay, so put on gloves, wear the apron, anything like that will get you one of the marks. You can't say put on gloves and wear an apron. That will not get you 2 marks. It would still be 1. Okay. The next thing that you can do is reduce the time that you're actually exposed to it for. So put it away as soon as you finished using it. And the third one is increase the distance. So use tongs, etc., to make sure it's not coming close to the body. So any of those will get you the marks. Normally it'll be a 2-mark question, so just pick any 2 that are easier to remember. Now, the next thing is how we're actually going to use these radioactive sources. So first one is smoke alarms, which is alpha particles. So what we've actually got with the alpha particles, then what we find is that we have this source of alpha radiation within the smoke alarm. Now that's going to ionize the air, which means there will be electrons flowing through the electrical circuit. Now, as long as that's happening, then the alarm stays quiet. However, if we have smoke, it goes up, and because alpha particles are the least ionizing, then what we find is they're going to be blocked by the smoke, the current in the circuit then drops, and as a result of that, the alarm then sounds. Beta particles are used in paper mills in order to work out the thickness of the paper there. So what we actually have is a source of our beta particles on top, a detector underneath, and then what it does is it counts how many beta particles make it through the bit of paper. If the count's too high, that means the paper's too thin, so it feeds back to the rollers and moves them further apart. Whereas if the count is too low, it means the paper's too thick, so it's going to then send a message to the rollers to move them closer together. So there's our beta particles. Can't use alpha particles because they won't go through the paper at all, and gamma particles, everything goes through. Gamma rays then we use in medicine, mainly killing cancer cells. So we use that idea of the gamma knife, which is obviously a source of gamma radiation that moves around the actual body so that it focuses all of the gamma radiation onto the tumor itself to kill it without killing healthy cells around the outside. We can also use gamma rays to sterilize hospital equipment, and we can also use them as medical tracers as well. Okay, so that's all about radiation. Last bit of P2 is just looking at the solar system. So first of all, hopefully you all learnt way back in year 7 the order of the planets working from the sun going out. So Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. If you haven't learnt them yet, then you've got to try and learn them by tomorrow. Foundation paper particularly, they do like to give you the odd 1 or 2 marks just for being able to identify the planets on a diagram. Okay, so whatever rhyme works for you, learn it, use it. If you're on the higher tier, then they do want you to know the force that actually keeps all the planets moving in their nice little circular path. Yes, that is my mnemonic there, Killjoy Jr. So what we actually find is that we have this idea of a centripetal force. Now, the centripetal force is going to keep all the planets going in that nice circular orbit around the sun, and it's all as the result of gravity. So gravity between the sun and all the planets, and between each planet individually. Okay. Now, other bits in the universe that we've got, going from the smallest, you have meteors, comets, black holes, planets, stars, galaxies, and the universe is the whole thing altogether. So what we actually have then is that we have all those different things that make up our universe. Hopefully you all know that we live in a galaxy called the Milky Way, which is actually made up of a huge number of stars. So what we actually have then is that the Milky Way itself is 200 billion stars. You don't need to remember the number, just know that there's a lot of them. And every single galaxy in our solar system, in our universe, could have that many stars. Okay. Now, what we find is that once we actually know all of these different things that are out in space, as all humans do, we want to find out more. So there are 2 options to us. First of all, we can use unmanned spacecraft. So that's where we're actually going to be sending out just these probes, which have various different sensors and all these different machines which will record large amounts of data and then send it back to us on Earth. or we could use the manned spacecraft. So they're the ones that we're putting humans on. So what we find is, with the unmanned craft, there are some pretty significant advantages. First and foremost, less maintenance. So if it breaks, no one's really going to care that much. Okay, it costs a little bit of cash, but it's not a case of it's going to be the end of the world. No one's going to die because there's no one on it. So the other thing that we can do with those is it's going to also be a big advantage to us, because we can send it into areas to take readings that we wouldn't actually be able to get close to without obviously having humans put in danger. Okay, so the manned craft that we could have then, these ones will obviously have humans on there. So if they're going to have humans on there, what we're going to find is it's going to have food, it's going to have oxygen, we're going to have to consider their health and well-being. And it's always good in order to bring them back home at the end. So what we actually need to do is think about what different things we need to build into that craft to actually improve their existence and make sure they come home at the end of it. Okay, does mean that we can fix it if anything goes wrong though. Bear in mind that space travel is not always safe. Many astronauts have died over the years just as a result of trying to either get off the launch pad or trying to re-enter the Earth. Now, next bit we've got is asteroids. So one of the questions they like to ask you is, what are asteroids made from? Simple answer, rock. So asteroids are the ones that are made of rock. So what we find is that they're all pretty random shapes because gravity is not strong enough to actually pull them into the spheres like all the planets. Now, what we find is the vast majority of them are actually found in the asteroid belt. And the asteroid belt is actually located between Mars and Jupiter. For those of you on the higher tier, you need to know why we have the asteroid belt there. And the whole idea behind why the asteroid belt exists and where it exists between Mars and Jupiter is because the actual force of gravity from Jupiter was so strong that it stopped those asteroids pulling together to actually make another planet. So just remember that on the higher tier, that the reason that we have the asteroid belt there is because Jupiter's gravity actually disrupted the formation of a planet and therefore left them as that big belt. In terms of the other type of object they could ask you about, we've got comets. Now, comets are made of ice and dust, okay? So that's the big difference. Asteroids are rock, comets, ice and dust. So remember the difference between them, okay? Now, what we find is comets are very obvious because when you see them in space, they end up with this big tail coming off as they come closer to the actual sun. Because as the ice melts, you get all of that tail made of all the ice and all the bits of dust that are being sent off into space. So remember, comets have that tail. One of the questions they do like to ask you every once in a while is about what happens when something hits the Earth, so when we get those collisions. So what we actually have then, as a result of anything hitting the Earth, the tail is made of ice. So it's ice and dust. So what we find is if anything comes down and actually hits the surface of the Earth, then we will have large amounts of dust thrown up into the atmosphere. Now, that dust can actually block out the sun, which is going to lead to things like plants dying. It's going to lead to rapid climate change. And we will also have very large fires coming from that impact as well. So what we find is some species may become extinct as a result of that. Think dinosaurs. So all those in my 11L2 that spent all year whistling the Jurassic Park theme to me, it's actually applying this time for once. Okay. Now, obviously what we want to do is obviously work out if we're about to be wiped out by some giant asteroid coming through space. But the big problem we've got is space is kind of big. So what we need to do is try our best to spot anything coming. So what we use are these very powerful telescopes in order to actually try to observe as much of the sky as possible, but it's not an easy task. So what we find is any of those asteroids that are actually up in space, they're really small and they move very fast. So that makes it very difficult for us to actually observe them in the first place. And it's also going to be problematic to actually see them for long enough to actually get their trajectory calculated. And a trajectory is literally the path it's going to take. So we basically work it out as to if it's actually going to hit us or not. So one other thing we need to know about is the formation of the moon. Okay, Now, the biggest theory that we've got on how the moon was formed was that at some point in the very distant past, then there was another planet that was about the size of Mars that decided it was going to collide with the Earth itself. So basically you had two planets colliding in rather large explosion, as you can imagine. All of those heavier elements like iron sank to the middle, and all of the lighter elements were thrown up into orbit, and over time they've come together, and that's our moon. And obviously we've gained evidence for that from where we've actually sent astronauts up to the moon and they've brought back samples. Then it doesn't have anything like iron there at all. So coming on to the actual formation of the universe, what we have is the Big Bang Theory. Okay, so the universe itself starts from this very small, very dense, very hot initial point, and then it had this giant explosion bursting out into everything. Now, everything began at that moment. Okay, please don't write onto an exam paper for science that it was caused by God, because I guarantee you will not get any marks for that. Okay, this is the point that you are going to be thinking you're sitting a science exam, no matter what your religious beliefs may be, then do not go and write those on there. Okay, because what you need to do is just focus on the fact that what we're actually looking at is a science paper. So the only answers that will be accepted will be the scientific theories. Okay, so just go careful with that. Now, we actually have two key pieces of evidence. Okay, first one is going to be the fact that those galaxies that are furthest away from us are moving the fastest, which suggests the universe is still expanding out. Okay, so literally the universe is expanding. It's bigger today than it was yesterday, and it'll be even bigger tomorrow. For those of you doing the higher tier, you actually need to know a little bit more. You need to know about this thing called redshift. Okay, so when we're talking about redshift, what we're looking at is the fact that the light from those distant galaxies, the ones from far, far away, then they have actually had their light stretched. So what we see is that the wavelength has been stretched, which means that it's moved to the red end of the spectrum, hence redshift. So what we find is, because the galaxies are moving further away from us, then the wavelengths of light are getting stretched, moving to the red end of the spectrum, and therefore that's what we see in our telescopes. Okay, so bear in mind redshift. Second piece of evidence that you all need to know about, whether you're on foundation or higher, is cosmic microwave background radiation. A big mouthful, but you can just remember it as CMBR. If you write CMBR, you get the mark. Now, no matter where you actually point an instrument to record it, you will find it. Anywhere at all in the universe, it's everywhere. So what that actually does is it supports the idea of the Big Bang, because as we're finding the radiation has been cooling, then it's also stretching. So today we're in the actual microwave region of the electromagnetic spectrum, and that's the same everywhere you look. Okay, higher tier again, this is only for the higher tier. Then what we can do with all of this information that we've got from CMBR, from redshift, etc., is we can use all of those different bits of information from those distant galaxies and then work out how old the universe is. So it's a load of maths, basically stupidly high level maths that no one really knows. The red end of the electromagnetic spectrum, so you've got the visible light, red end is one end, blue end is the other, and then it's literally shifting it through the electromagnetic spectrum. Okay, now as a result of all these calculations, then what we've found is that the universe is approximately 13.7 billion years old. Again, you're not going to need to remember the number, but it's how we've actually worked it out. Last part of our P2 then, before we do the little theories, is the life cycle of stars. So the bit that everyone absolutely hates. So what we have then is all of the stars that you see in the sky are actually formed the same way. Okay, so what we have at the very beginning of every star's life is this thing called a nebula, which is quite simply a huge cloud of gas. Now gravity pulls it all together, and that makes our main sequence star. Okay, for those of you on the higher tier, you need to a little bit more detail. Okay, so you start with a nebula, just as we said, and then it gets denser as more gas is pulled in. Okay, so what we actually find is that as more gas gets pulled in, it gets hotter and hotter and forms this thing called a protostar. Okay, now what we find is that protostar continues to grow larger, and eventually we end up with it getting so hot that we have nuclear fusion taking place. So fusion is where the nuclei atoms are joining together, okay? That's our main sequence star, and that's where our sun currently is, its main sequence, okay? Again, still on the higher tier here, what we find is that this is a sequence that's going to last for many millions of years, okay? So the main sequence is like the main part of the star's life cycle. Then what we come on to, which again, Foundation and higher need to know, is the star death. So literally what happens when that star comes to the end of its life. So what we've got, two options, small stars and large stars. So for the small stars, and our sun is classed as a small star, then what we find is that it cools and expands to become a red giant, first of all. So what we find is that the red giant is then going to expand out, and what we find as a result of that is some of it is going to break away and make a planetary nebula, and the other bit is actually going to then just be the core of the star. And that little white dwarf is the core of the star, and that remains. Over time, it'll cool and eventually just fade into nothing, and that's the end of our little stars. The big stars, so the ones that aren't actually our sun, then what we find is they will still follow the same process of cooling and expanding, but the problem there is that they're going to grow much bigger. So they turn into what's called a red supergiant. That can then explode in this thing called a supernova. And then as the core of that star is crushed down by these huge gravitational forces, then we end up with this thing called a neutron star. Okay. Now, the neutron star actually we can record because it sends these pulses of radio waves to Earth. So we can actually kind of hear the neutron stars, if you like. If we have a very, very large star, then what we find is, as opposed to becoming a neutron star, then it's actually going to end up as a black hole. And black holes have incredibly strong gravity so that nothing actually escapes, okay? In terms of the black holes for the higher tier, just remember that it's basically the fact that they have these near infinite densities because they've got such a tiny volume and such a large force of gravity that literally nothing can escape, hence black hole. Very, very last bit of our P2 is just looking at the fact that we actually have different ideas on the theory of the universe and how it's actually formed, okay? So first of all, we go back to the good old times of the ancient Greeks. Can't beat the ancient Greeks for sitting there and coming up with the most random ideas about science ever. So all those blokes sitting around with their togas, stroking their beards. Then we have Aristotle, first of all. And Aristotle's whole contribution was Earth is the center of the universe. Just decided that one day. Then we come on to the one with the weird name, Ptolemy. Now, he's the one that begins with a P. Doesn't look like it's actually pronounced Ptolemy, but it is. And he also believed that the Earth was the center, but he also followed this up by saying that all of those stars that you can see are actually this fixed background of unchanging stars. Again, now we look at them and think, what ridiculous theories. Now we come a lot further into the more recent times to Copernicus. Now, he actually was the first one to take some measurements. Revolutionary idea in science. So he actually sat there, he took measurements of the planets, and then he used models to actually describe their motion. And the only way he could actually explain that is that the sun was at the center of the universe. So what we find is that this is the shift now from the Earth being the center to the sun being the center. But he didn't publish his ideas until his death. And as always with science, when people don't publish their ideas, it's basically down to religion. Now, Galileo is the other one that's also taken a lot of observations. And what we actually find is that he observed the moons around Jupiter first and foremost. Now, that was proof that not everything orbited Earth because we saw the moons going around Jupiter. So that meant we had that bit of evidence. And he also saw stars changing. So he saw supernovas that proved they weren't this fixed background. And then finally, we have Newton, who then gives us the whole theory of gravity to explain everything. So that is all of P2. So I think I've now covered all of radioactivity, dynamo effect, Big Bang, man versus unmanned collisions, near-Earth objects, the life cycle of stars. Next one is going to be chemistry then. So C2 is going to be next for us all. Starting off with one of the requests that I had, which was all about the actual structure of the Earth. So structure of the Earth, quite simply, is just the fact that around the very outside, you've got the crust, then the mantle, then you've got the outer and inner core. There you go. I even drew you a lovely diagram. So crust around the outside, mantle's next one in, then the outer core, and finally the inner core. Okay. Now, what we find is that we can't actually study the structure of the Earth directly, okay, because it's too thick, and basically when you get through the crust, then the big problem is it's going to be too hot, and therefore what we're going to find is scientific instruments are not going to work, okay. So what we use are seismic waves in order to study it, okay. Now, what we then have is that the actual crust of the Earth itself is broken up into these things called tectonic plates. So tectonic plates are the bits that are floating around on the mantle, moving really slowly, about 2.5 centimeters a year. Okay. Now, the reason they're moving is because we've got these convection currents in the mantle. So again, it's hotter at the center of the Earth, cooler towards the top. So what we find is you have that nice little flow of the mantle, and the tectonic plates floating on the top then move. Okay. If you're doing the higher tier, you need to understand this idea of subduction. Okay, so the oceanic and the continental plates. So the oceanic plates are the ones that are actually going to be the more dense of the two. Okay, so oceanic plates are denser than the continental ones. So what you find is where you've got those two plates, if this is your oceanic one and that's your continental, then the oceanic plate, because it is denser, is going to be pulled underneath. So as the plate goes underneath, then it melts. Okay, so this is where we're going to find volcanoes occurring, for example. So we will also get earthquakes at those plate boundaries, because where the plates meet, they're going to catch on each other and then eventually push past with this big release of energy, hence our earthquake. Now, what we've had a whole range of different ideas about basically the nature of the Earth's surface, but we do accept the theory of plate tectonic now, because it explains a lot of different evidence that we've got. For the higher tier, you do need to know a little bit more about this. So you got Alfred Wegener, who published his ideas on this thing called continental drift. So he basically said at some point in the distant past, all of the continents were all joined together, and then as time's gone on, they've moved away from each other. Okay. Now, basically, no one actually believed him for about 50 years, because we couldn't explain basically how this happened. He kind of said, this is what's happened, but he couldn't explain how until the 1960s. That's when we actually got the evidence of seafloor spreading and subduction. Okay. Now, what we find is that when we're looking at things like volcanoes, we come straight up to igneous rocks. So what we've actually got then are magma and lava. You need to know the difference between them. Magma is the molten rock under the Earth's surface. Lava is molten rock above the Earth's surface. That has actually come up once before as a question on the foundation tier. Now, what we find is igneous rocks are really quite easy to identify because they're made of crystals. So those crystals lock together, and that's what gives them their strength. And the size of the crystal depends on the rate of cooling. Okay, so what we actually find is that if it cools quickly, we make these very small crystals, whereas if it cools slowly, makes much larger crystals. So what we find is just by looking at the size of the crystals, we can work out basically how quickly it cooled. One question they do like to ask every once in a while is just basically about why people live on the slopes of volcanoes despite the fact it's dangerous. And the key reason behind that is that the volcanic soil is fertile, so it grows a lot of crops. Not all volcanoes are as dangerous as each other, though. Some actually are much more dangerous based on the types of lava. So some of them will erupt with this thick lava, which are the more violent ones, and they tend to be a lot more dangerous. The ones that erupt with the runny lava, you can outwalk them. They're the ones you find in Hawaii, where it just constantly erupts this slow flow of lava that you can just go and have a nice little tourist attraction and have a little look at them. We will have these people called geologists who study volcanoes for the whole purpose of learning about the Earth structure and trying to actually predict any of those future eruptions to save people. Okay, so that's the Earth structure done. We obviously have a few things about construction materials, but I'm not going to spend any real time on those because a lot of it's common sense. basically we're going to use different things to make different objects based on the properties that they've got. Okay, for the higher tier, you obviously need to remember the fact that you've got limestone, marble and granite. Remember that limestone is the softest of the rocks, with granite being the hardest. Okay, now what we find is that all of these rocks that we're going to get will be dug out of the earth in things called quarries. Okay, so any of those quarries that we have today are actually going to have a few key problems with it. First and foremost, they're going to be noisy, they're going to be dusty, and they can destroy the landscape. Okay, the benefits though, they can actually provide jobs and they can also provide valuable resources. Okay, so any of those will get you marks there. One question I do like to ask you is about thermal decomposition. Okay, now thermal decomposition, if they ask you for a definition or what is thermal decomposition, it's just when one substance is broken down into two or more products by heating. Okay, so what you actually need to do there is make sure you specify the fact that it's starting off as one substance, becoming two or more, and it's only heating that's actually doing that. I have actually seen them do questions before where they've given you an equation and asked you what kind of reaction it is. If it starts with one product and there's two or more on the other side, then thermal decomposition will be your answer. So what we actually find then is one of the very useful things that we can make by heating up our calcium carbonate. So CaCO3 is calcium carbonate. When you heat it up, we're going to break it down, first of all, into calcium oxide, and secondly, into carbon dioxide. Now, calcium oxide is quite useful because what we can do is just add water to it to make calcium hydroxide, which is lime water. So what we find then is that lime water is very useful because we actually use that to detect carbon dioxide. So hopefully remember that if it asks you how do you test for lime water, it is just going to be a case of it's going to go from colourless to cloudy. Okay, so remember lime water goes from colourless to cloudy for carbon dioxide. If you're doing the foundation paper, anything they're asking you in terms of equations is going to be word equations. If you're doing the higher tier, that's where you can get the balanced symbol equations. Okay, now what we're actually going to come on to is the fact that there is on my PowerPoints, you can look at it yourselves, okay? But there are all these different things we can do with calcium carbonate. So you can obviously use it to make mortar, to make concrete, to make cement. Make sure that you know what you add to it in order to do that. One thing that we will have is when we've made concrete, it's okay, but we can make it better by reinforcing it. Okay, so if you actually put a steel mesh and then pour the concrete, basically we have a composite material, so it's a reinforced material. So that means that it's going to be hard and strong in compression, but it's also going to be flexible and strong in tension. So it's got the best of both worlds. Now, our next bit leads us very nicely onto electrolysis, which is obviously one of those bits that for some reason you all seem to hate and never understand, even though it's not that complicated in reality. Okay, so first of all, we need to look at the idea of copper. Okay, so copper is one of those chemicals that we use an awful lot of in a whole range of different things. So first of all, think about the basic properties of copper. It's a metal, so go with any property of metal. Okay, so good conductor of heat, good conductor of electricity. It's going to be ductile, it's unreactive, anything like that is a brilliant property to use. Okay, now what we find is that when you actually extract copper, it's not going to be pure. Okay, so what we're actually going to have to do is purify the copper. Okay, now we do this using good old electrolysis. There you go, another delightful diagram for you. So what we have are two electrodes. You've got the anode, which is the positive one, and the cathode, which is the negative one. So think of the big negative cat, the one I always show you, the angry cat. So remember that one. Now what's going to happen is as you pass electricity through this, then what we're going to find is we're going to have our impure copper. Okay, so remember we've got impure copper, and then we have our pure copper forming on the other one. So what we are going to have then, people need to stop swearing. Otherwise I will literally shut down the chats and then you won't be able to ask for anything else in there. So what we have, once you pass electricity through, then we have our impure copper anode, and then that's going to dissolve, and then it's all going to be pure copper on the cathode. So what we find is that just passing electricity through this is going to actually allow us to get a nice pure copper. So for the higher tier, you actually need to know a little bit more, okay? So the solution that we've got there is called the electrolyte, and that's actually going to allow the solution to conduct the electricity. So what we find is that during electrolysis, then the copper is deposited at the cathode, and that's going to gain mass. Because the anode is going to lose mass, because it's going to lose the copper. Okay, so common sense hopefully comes into play at this point. For the higher tier, you do need to know those half equations. So obviously those of you that did the coursework on it, you got a bit of an advantage. For those of you that didn't, not so much. So what we actually have then is, if we're thinking about the reduction reaction first of all, okay, so go back to oil rig, okay, so oxidation is loss of electrons and reduction is the gain of electrons, okay. So what we find is that if you've got your copper ions and they gain 2 electrons, they make copper atoms. That is a reduction, okay, whereas the copper atoms that lose 2 electrons become copper ions, and therefore oxidation. Okay, so make sure you remember the way around that they go. Now, the reason that we're going to be carrying out electrolysis is obviously to get the pure copper. The big downside is that an awful lot of the ores that we've got left aren't exactly the best. Okay, they're quite low in the amount of copper that they've got, and they're getting more difficult to mine. So what we actually find then is that we're actually finding it much better to actually recycle copper than to extract it from its ores. Okay. Now, the next one you've asked me to go through, I'm going to do electrolysis brine later on. So what we're going to do then is electrolysis brine comes later on, but we're going to have a look at metals and finish it off. Folks, you need to actually stop swearing now. Otherwise, we'll just call it for the night now. And then literally, that'll be it. I also won't run the seminars for the Unit 3s or the Unit 4s. Quite simple. So either you pack in the swearing, or we stop now and we don't do it for any of the other units, because I'm not going to keep blocking all of these people, because it's really not worth my time, folks. Your choice. Right, so alloys are next then. So what we've actually got then, if we have alloys, then we're talking about a mixture of 2 or more elements where at least one is a metal. Okay, so quite simply, if you've got anything with 1 metal and something else, or if it's 2 metals, etc., then that's fine. Okay, so they are all examples of alloys. You need to know 3 examples. First of all, you have amalgam, okay, and now this is the stuff that if you've got any of those silver fillings in your teeth, which hopefully you don't, because, you know, you're 15, 16, then what you need to do is obviously you need to have a filling put in there. Now, what you've actually got then is the fact that amalgam is going to be used in the fillings of the teeth, but its main metal is actually mercury, okay? So the second one, we've got brass, which is made of copper and zinc, and that's used in our musical instruments and our coins. And then what we've got are also solder, which is what we're going to use to join electrical wires. So anytime you've done any kind of electrical circuit work in things like technology over the years, you've used that solder, the stuff that's really easy to melt, okay? So the only thing you need to know for amalgam, the main metal is mercury. For brass, the main metals are copper and zinc. And for solder, the main metals are lead and tin, okay? So what we need to remember are their uses, the main metals, and their names. Quite often, this will be one of those little joining line ones that they like to do for you, okay? So what we find is that alloys are generally better for the simple fact that they're usually stronger and harder than the metals, okay? So what we find is the fact that if you take brass, for example, because it's got copper and zinc atoms, which are different sizes, then basically it means they're not going to slide over each other easily, which makes it obviously a much more stronger material and makes it better in terms of coins, which you don't want to bend out of shape in your pocket. If you're doing the higher tier, then you need to obviously know about the smart alloys. So shape memory alloys are one of those examples. So they're things like your glasses that you might have. So if you've got those glasses that if you sit on them, they go back to their normal shape, that's one of those smart alloys. Okay. So remember, for the higher tier, that is one of the important ones we've got there. Corrosion is our next little bit, which is quite simple. Basically, things will corrode over time. Okay. The only metal that can rust is iron, nothing else. It only corrodes. Okay. So what we find is that if you've got acid or salt present, then what we actually find is that that is going to mean that it happens faster. They do occasionally like to give you a question which is talking about the difference between iron and aluminium. Now, what we actually find is that iron and aluminium will have different properties. Okay, so what we find is that with our iron and aluminium, if you are given any of these questions, you will find that they have a table with various information, and then all you need to do is just use the information to work out what's actually best. Okay, so quite simply, if it's in aeroplanes, aluminium is probably going to be the best because it's got a lower density, which means it's more lightweight. Okay, so just to use a bit of common sense there, and you'll be fine. Now, what we find is that they could also give you something like, you know, what would we use to make car windscreens? As shocking as that is, that has been a question before. And you would obviously just sit there and talk about the fact that it's going to be made of glass because you can see through it. So just common sense comes into play for a lot of that. When we're thinking about our next one that was on my list, the Haber process. So the Haber process is how we actually make ammonia then. So in terms of making ammonia, what we actually find is that we're going to start off with nitrogen and hydrogen. So they're the two gases. And when we apply heat and pressure, what we're going to find is the fact that we have the ability to then join it together, and that makes ammonia, which is a very important chemical. Now, when we're thinking about factors that affect the cost of making chemicals, first and foremost, the cost of the starting material. So how much the raw materials cost. Secondly, you need to think about the fact that the equipment has its own cost. Thirdly, you need to think about the actual cost from the people you're going to have to employ. And then you also need to think about the energy that's involved as well. So the only thing I will say here is look very carefully at the fact that when you are trying to decide what you should be using in your answers, you've got to think very carefully about what the question has already said. So do not write down the cost of people's wages and electricity, because quite simply, if it's got in the question other than the cost of electricity and you write it down again, then what you're going to find is you're getting only 1 out of the 2 marks. Quite simple. So just use some common sense at this point. So once you've actually looked at the information, you can make those decisions. Now, ammonia itself is one of those chemicals that is incredibly important in terms of the world, because ammonia is used to make a lot of fertilizers, and fertilizers basically give us enough food to feed the population. So what we actually have first and foremost is you need to know the reversible reaction sign. So that is reversible reaction. If it comes up and asks you what it means, just say reversible. Okay. Now, what you actually find is that they have asked you in the past about where we're actually going to get the hydrogen and the nitrogen from. So first of all, you've got the hydrogen comes from the cracking of oil fractions, or it comes from natural gas. And you've also got nitrogen from the air.